This figure shows you an involute geometry. For the purpose of analyzing stress and the diffraction of gear teeth, it is important to be able to compute the thickness of a tooth at any radius. For this figure, the arc distance AB is equal to the linear distance BT. Therefore, AB is equal to RB times of C. C is the rolling angle. Key is called the involute function of C. It can be written involute of C. Actually, we can use the involute function to compute the thickness of the tooth at any radius r. This slide shows you how to determine the tooth thickness at any radius r. We know the tooth thickness Tp at the pitch circle equal to pi over 2 times diametric pitch and the pressure angle phi. From the involute geometry shown in this figure, we can get the tooth thickness Tp is 2 times Rp times alpha minus involute function of phi. Then we can get the value of alpha like this. At any general location defined by R, we have the tooth thickness T is defined by this equation. We already know the angle alpha. If the angle beta is known, we will get the tooth thickness T. From this right triangle, we can get the angle beta equal to arc cosine of RB over R. This problem is to determine the thickness at addenda and the base circles of tooth. The gear have diametric pitch 4, 13 teeth, and the pressure angle 20 degrees. The tooth thickness at the pitch circle equal to half the circular pitch. We first compute the radii Rp, Rb, and Ra at the 3 locations for which the tooth thickness is desired. From the equation of the textbook, we can get the radius of the pitch circle Rp and the radius of the addenda circle Ra, where Ra is equal to Rp plus addenda A. We can compute Rb by Rp times cosine of phi, and from table 11.1, the circular tooth thickness is half the circular pitch, so we have the value like this. Parameters Ra and Rb are known, so we can compute the angle beta A at the addenda circle. It is equal to 28.2 degrees. And compute the angle beta B at the base circle. It will be equal to 0. Using equation 11.20 of textbook, we can compute the tooth thickness Ta at the addenda circle and the tooth thickness Tb at the base circle, like this. This problem is to determine the maximum radius of a addenda circle if a non-standard gear is used. From the last example, 11.2, the gear tooth thickness becomes smaller as the radius decreases from the base circle. We can use the condition that the gear tooth thickness becomes 0 to determine the maximum radius of the addenda circle. From equation 10.20 for the tooth thickness, we have this relation like this. Parameters TP, RP, and phi are known. Then we can get the involute function of beta equal to 0.0673. We need to compute the inverse of the involute function of beta. This website provides an inverse of the involute function calculator. Let us visit this website. I input the involute function 0.0673 here and click the execute button here. We can get the angle beta equal to 13.1737 degrees. We know R is RB over cosine of beta, and beta is 32.13 degrees. So we can get R equal to 4.161 inches. The internal gear is a gear with its teeth cut in the internal surface of a cylinder and meshes with external pinion gear. The addenter circle for the internal gear is inside the pitch circle, and the tooth profiles are concave rather than convex. Internal gears are commonly used in planetary gear systems and the compact gear box. This figure shows you a planetary gear system. Both the pinion and the internal gear rotate in the same direction. We can compute the parameters of the internal gears using the same equations as for external gears. The advantages of an internal gear set is the gear system is compact. There is lower contact stresses because the teeth of the internal gear are concave and the greater length of contact possible between mating teeth. There are three different types of interference can occur with internal gears: involute interference, Trochoid interference, and trimming interference. For the design of gear trends, we need to avoid the first two interferences. But for manufacture, for example, shaping cutters, we need to avoid all the interference. This slide shows you why involute interference happens. The line of action is tangent to the base circle of internal gear at point C and to the base circle of the pinion at point B. If contact occurs between points B and C, interference will happen. Because the involute part of the pinion tooth starts at point B of the base circle, there is no involute when the radius is smaller than the base circle. We call it involute interference. Point A is the intersection of the line of action with the addender circle of the pinion. Therefore, the length of the line of action is AB. To avoid the interference, the addendum of the internal gear shall not extend beyond point B. This slide shows you trochoid interference. If the difference between the numbers of the teeth of the two gears is small, the pinion tooth will interference the internal gear tooth at the points A and B. We call it trochoid interference. And this slide shows you trimming interference. If there are too little difference in number of teeth of the two gears, the pinion can slide in or out axially but cannot move radially. We call it trimming interference. This interference only should be considered for manufacture. For example, the shaper cutter needs to withdraw radially when gear shaping, so we need to select the smaller shaping cutter to avoid the trimming interference. Later, we will talk about gear shaping. If the path of contact extends beyond the point of tangency with the base circle of the pinion, we call this point the interference point. The tips of the teeth on the gear come into contact with portions of the pinion tooth profile inside the base circle. Because the involute is not defined inside the base circle, conjugate action is lost, and the tips of the gear teeth will interfere with the lower portion of the pinion teeth. The left figure shows a rack cutter generates the peer profile. If interference happens, the pinion is generated with a rack-type cutter or hob. The cutter teeth will undercut the pinion teeth and weaken them. The right figure shows you the normal profile and the undercut profile. In the following slides, we will talk about interference and the undercutting locations. This figure shows you two gears are in mesh. The interference point on gear 2 is point A, and the lead on gear 3 is point D. The addendum circle of the gear 3 intersects the line of action at point B, and the addendum circle of gear 2 intersects the line of the action at point C. If the addendum circle for gear 2 is tends beyond point D, or the addendum circle for gear 3 is tends beyond point A, interference will occur. Actually, we need only investigate one of these conditions, because interference will always occur first on the small gear. In this case, gear 2 is larger than gear 3. Therefore, we need only to check points C and D. If the pitch diameter of gear 2 becomes larger, point C will gradually move toward point D. If point C extends beyond point D, interference will happen. So, if gear 2 is actually a shaper cutter, the material in the interference region of the pinion will be removed. Then the pinion will be undercut. The undercut pinion have high stress in the root region. They may cause gear bending failure, like this picture. The worst case for interference of undercutting is when the pinion is meshed with a rack or generated with a rack cutter. Therefore, if we design the gear to avoid interference with a rack, the gear will mesh with all other gears of the same pitch. Undercutting becomes more severe as the number of the teeth is reduced, because for given diametric pitch, The pitch diameter decreases when the number of teeth is reduced. So, there will be a minimal number for the tooth number to avoid interference. This slide shows you how to calculate a minimal number of teeth to avoid interference. This is very important for gear design. We may use K over diametric pitch as the addenda A for a standard gear, where K is constant. K equal to 1 for forward dip gears and 0.8 for stop tooth gears. The minimal number of teeth to avoid interference can be determined by identifying where a addenda line of the rake cutter extends beyond the interference point I on the gear. Using the geometry in this figure, we can compute the value of view like this. ORP is equal to A over sine of phi squared. We know RP is N over 2 times PD, and A is equal to K over PD. Therefore, we can get the minimal number of teeth like this. This table shows minimal number of teeth to avoid the interference in standard gears. The minimal number of teeth varies inversely with the pressure angle. Why? This is one of the reasons that larger pressure angles are often used. For 20 degrees pressure angle and full depth gears, the minimal number of teeth to avoid undercutting is equal to 18. If we want to avoid undercutting when the number of gear teeth is smaller than 18, a profile shifter coefficient X is applied. If you're interested in a profile shifter coefficient, please visit KHK website to see the detail.